Okay, the very first condition I want to talk about that is that assume we have a RC circuit that's made of resistance and capacitor, and then assume that circuit is fully charged, and then I want to see how it's going to get discharged. So how it's going to work? So assume I have a circuit, for example, like that. So assume I have a battery connected to a circuit, the RC circuit, which is a capacitor, single capacitor, and there is a single resistor like that. Assume I have a circuit like that. So it's going to be a key here, and there's going to be a key here. So at the t before 0, when the time is before 0, I'm going to close that key and leave it like that. When I close that key, what's going to happen is that this capacitor is going to be charged. So it's going to get charged and charged. And because that key is open, nothing goes through the resistor. So it's going to become charged like that. So it's going to be fully charged. After it's fully charged, what I'm going to do is that I'm going to open this key. So the key is going to be open after it's going to be fully charged. And then I'm going to close this key. So I'm going to make it like that. So after it's fully charged, I disconnect the source. So the source is not there anymore. So I fully charge the capacitor. I disconnect the source. And what I'm going to keep is going to be only the capacitor, the key, and the resistor. Okay, so let me bring it a little bit lower. So I remove the source. So the source is not there anymore. The capacitor is already fully charged. It's fully charged like this. So this is what we have, and so it's going to be it's the RC circuit. As I said, it's going to be R. So it has a resistance of R, and it's going to be the C. So it has a capacitance of C. And when after we charge that, we want to see what's happening. So at t is equal to 0, this is everything is like that. At t is equal to 0, I'm gonna close the key. Exactly at t is equal to 0, I'm gonna close that key, and then I want to see what happened in this circuit. Basically, what's happening is that it's fully charged. As soon as I close that circuit, in very short period of time, this capacitor is going to get discharged. In other words, the energy is already stored in it is going to be released, goes through the resistance, converted to heat, and then it's all dissipated away. So that's what's going to physically happen. Is that when I charge the capacitor, basically I store the energy in the capacitor. Now my capacitor is fully charged and has the energy already stored there. As soon as I close the key, all the energy stored in the capacitor is going to go and dissipate it through the resistance, and we'll see how it's going to happen. So if I want to analyze this system after it's closed, I'm going to use the node voltage method, and so I assume that, let me bring this a little bit lower. So assume that, so it's a T is 0, or let's put it here. There's a T is 0. So in node voltage method, I have to choose a reference. I'm going to choose this point as a reference. And then I want to write the node voltage for this point here. This point is connected, if you look at it, this node is connected to the V, to the C, and the other end of this, the capacitor is connected to the reference. So if this is 0 here, one end of the capacitor connected to the reference, the other end, the voltage in the other end is the same as the voltage in the capacitor. So it's going to be VC here. And eventually, so what we have here is that, remember when we have a node voltage method, we says choose that node and assume all the current leave that node. So I assume there are two current leaving that node. So it's going to be I1 and it's going to be I2. So two currents leaves that node. Now if I go ahead and write the KCL, remember we write the KCL at top node that we have. It was that sigma I should be 0. It was how we did it with the node voltage method. Basically, we assume all the current leaves the nodes, and then if we add them together, it should become 0. So I1 plus I2 should become 0. Now we know from previous chapter that the current that goes through the capacitor, remember, for capacitor, we know that the I is equal to C, the voltage in the capacitor over time, dt. That was what we had in the previous chapter. So this is current in the capacitor. So instead of I1, I can replace I1 with this equation. This is what is going. So I'm going to just put it I1 here. So for the I1, I would say that it's going to be C, and then the VC over time, whatever it is, over dt. This is how this is the I1 that goes through the capacitor, and the I2 is as what we had before. Is the voltage at the beginning minus voltage at the end divided by resistance between them. So I2 is voltage at the beginning, which is VC. Voltage at the end is 0 because it's a reference, and divided by R. This is what we had before in node voltage method. So it's going to be VC divided by R is 0. So this equation, let me make it VC, so divided by R, so equal to 0. So this equation shows us how the voltage at the capacitor is going to change over time. This is what we have. So we have, if we want to know, after I close the key, this the capacitor is going to start to decharge, and all of its energy goes through the resistance. And basically, it starts to have whatever voltage it has at the initial condition. That voltage is going to go all the way drop to 0 because all the energy is going to dissipate. This is the equation shows how that voltage is going to change from the time that we close the key to the time that all the energy is going to dissipated away. So when we want to do that, this equation, if in one of those whatever courses that they're teaching you the differential equation, I'm just, as a reminder, I will write it here. If you have the differential equation that is like that, it's the dx over dt plus alpha x is 0. If this is the equation, the answer for that equation is x is k e to the negative alpha t. So for detailed that refer to your differential equation course. So you can see that. If you have a form of equation that is in this format, then the answer for that format is going to be like that. So look at here. If I want to make this equation to look like this format, what I would do is that I would go ahead and times the all side by r. So it's going to be rc. Then I have dv over dt plus v. Yeah, so it's a vc plus vc. It's going to be 0. And the answer for this question, if I'm going to make it equation 1, the answer to this question has the format of, I would say it's going to be the VC, like the here is here, has the format of K e to the power of ST. So V is the voltage, T is the time, K and S are constant that we have to find them. The same here, that's the K, that the K is the constant that we have to find. So K and S are constant that we have to find these two. So that's the equation number 2. One more time, so I walk you back through that. So we write the node voltage method for the very top node here. Then we comes up with this differential equation, which shows the change of voltage through time. Now we need to solve this. We need to solve that to get the answer, to see how the voltage change. So if I rearrange the equation, so I times all the parts in R, the differential equation is going to be look like this. Now I need to solve that differential equation. The solution to that differential equation is this second equation. It's what we have done here. This is the solution of this differential equation. So this solution shows how the voltage is actually changing in that capacitor. Now I need to solve that solve this equation. This is the solution, but I need to find the K and S in order that I can use that as a solution. So if this is a solution for if the equation 2, if there is the solution for the equation 1, I can implement it in the equation 1 because this is a solution, so it should satisfy the equation 1. So I go ahead and replace 2 in 1 because the 2 is the solution. So if I replace 2, equation 2 in equation 1, what I'm going to get is that I'm going to have RC, then I'm going to have d over dt. So instead of VC, I'm going to put this value, K E S T, plus, again, instead of VC, I'm going to replace it with that. So it's going to be K e to power of ST, should be 0. So this is the equation I have, and if I go ahead and solve it, so it's going to be the RC, and then for this part, if I do the differential equation here, so it's going to be K S e to the power of ST, and for here it's going to stay the same, so it's going to K e to the power of ST is going to be 0. So, and now if again I rearrange this equation, I rearrange it in order that I have the this part out. So I'm going to have the R I have here R, C, and S plus 1. So it's R, C, and S, and then the rest is going to be K e to the power of st is 0. So I'll see if I'm right. So yeah, it's R, C, and S, and then yeah, so it's going to be look like that. So this, now I want to solve this equation. Look at this equation. This second part here is time dependent. The second part, this part here is time dependent. So it's going to be changed over time. So the only way that this equation is going to be 0 is that this part should be 0. Because the other part is going to keep changing. It's not going to stay constant. So this part, the only way that this equation can be 0 is that this part, this constant part becomes 0, because this is a time dependent. As the time change, it's going to change, and it's not going to be 0. As you can see, whatever I put here, the time is going to keep changing and changing and changing. This term is not going to be 0, and also it's changing. So the only way that's going to be 0 is that this term inside the parentheses should be 0. Because of that, so that RCS plus 1 should be 0. And from there, remember R and C are known, because R, we know the resistance, whatever resistance we use. The C is the capacitance. We know whatever capacitance we know. So R and C are known. S is the one that is unknown. And so we want to find this. If I get this. So the unknown we have, again, if I come with the unknown we have is the K and S. These two, K and S, are unknown in this equation. This is our solution, and we want to find that solution. In that solution, K and S are unknown. So here, S is going to be -1 divided by RC in that case. So this is the S. So now we know the S. We have to go and find the K, because S is known. Now we have to go ahead and find the K. To find the K, if we want to find the K, look at here. I know that at the at the time is 0, when exactly the time is 0. This capacitor is fully charged, and whatever voltage it has, and assume the voltage it has is the initial voltage. So I'm going to put it VI here, or at the time 0. So I'll put it here probably better. So that when I charge this completely, the voltage here has become VI after it's fully charged. So I know at the time 0, when I put this here, it has that initial voltage in it. So the initial voltage in the capacitor is VI. So I know that. So at T, I know that the voltage in capacitor is VI. Is whatever initial voltage it has when I fully charge. And we know that value as well, because when we charge it, we know the battery. So when we charge it, we know how much voltage it's going to have after it's fully charged, that capacitor. Now that it's fully charged, and we know that the voltage is that, right after that, and usually they put it as a positive or negative. If I put it positive or negative, it means that right after 0 or right before 0. If I put negative, it means right before 0. If I put positive, it means right after 0. So right after I close the key, just close the key. So let me assume I just close the key. So I'm gonna make it, instead of T0, I'm gonna make it right after I close the T. So I just close the key right after that. So still there's not gonna be change in the voltage in capacitor. So right after I close the T, still you can consider it 0. I know the voltage is VI. Now here, go back, I can go back and look at it. This is my solution. Equation 2 is my solution. So if I go in equation 2 at T is right after I close the key. So I know that VC right after I close the T is VI. So instead of VC, I put the VI right after I close the key. And then the K is K, E is E, the S, well, whatever it is. So we know the S, the magnitude of S is that, and the T is 0. And times 0. So this E to the 0 is become 1. So therefore, it's going to tell me that K is going to be equal to VI, the initial voltage that I have in the capacitor. So now if I put these two together, if I go ahead, so if I substitute all of these in my solution, so I have to let's go to the next slide. If I put all of them in my solution is going to be the voltage at capacitor over time is going to be VI, the initial voltage in the capacitor, E to the power of negative, let me put it here, negative T over RC. So if I substitute the K and S in the previous one, so if I go back in previous one, if I substitute K and S, the S is negative 1 over RC and the K is VI. If I substitute them, this is what I'm gonna get. This is gonna be my equation. And usually the RC is gonna be shown with tau, is the Greek word of tau, is similar to T, and is called time constant. Time constant of this is called time constant. And so then usually is gonna, this equation, the solution to that is gonna be written as, is gonna be VI e to the power of and then to substitute the RC with that. So it's gonna be negative T over tau. And that is the solution that shows how the the voltage in that circuit that we had is going to be discharged. So this is a solution. It will show how it's going to discharge. Basically, that shows that is here after I close the key, and then when I close the key, the voltage in this capacitor from fully charged starts to drop eventually until all the energy in that capacitor is going to be dissipated and becomes 0. And this is the equation, shows that how that voltage starts to drop from the initial voltage when it's fully charged to become 0. If you plot that equation, this is something that you will get something like that. If I can. So if I draw that. So it's going to be the time, and it's going to be the VC, the voltage in capacitor. So initially the voltage in capacitor is at VI, so it's fully charged at VI. And as soon as we as soon as here we close the key, that voltage, as I said, is going to drop because it's going to lose the energy to that resistance. So it starts to drop, and it's going to start to drop something like that. So it's going to start to drop. Well, let me see if I can draw it better. So let's start to drop exponentially, something like that. And it says that for I would say for t equal to 5 times of tau, when the time becomes equal to 5 times of tau, that VC is almost 0. So after 5 times of tau, whatever is the tau, the 5 times when the time is equal to 5 of the tau, your voltage is almost all gone. It becomes 0, and so that's how it gonna work. So that's a very first transient, probably the simplest transient that we have. So one more time, very quickly go over that. We have the capacitor. We fully charge that capacitor. Then after we fully charge that capacitor, we remove the battery and we connect the capacitor to resistance. As soon as we connect the capacitor to resistance, the capacitor starts to lose energy, and it starts to its voltage starts to drop. We want to see how the voltage is going to be dropped right after we connect it to the resistance. So we write the node voltage equation, and eventually we comes to this differential equation. The solution to that differential equation is this second equation, and so we want to find this solution. That's what we are looking for. So we do it in 2 steps. The first step, because this is the solution, we can substitute it in the original equation, and it should satisfy the original equation because this is the solution. So we substitute it there, and from there we can find the S. The second one is the initial condition, is that when the T is 0, at the time that T is 0, the initial condition, the initial voltage in the capacitor we know is equal to whatever it was when it was fully charged. So if the time is 0, the voltage is the voltage that is fully charged. So we do that. We replace that initial condition in the second equation, and from there we find K. And then we just replace S and K in that solution. So this is what we will get. Okay, let's look at an example. Assume we have the capacitor connected to the resistance and it's fully charged here. And then we want to see if I close the key, how long is it going to take? So what's the time? How long is it going to take? So the VC becomes equal to 0.25, becomes 2.525 volt. So initially we know that the voltage is 100 volt. When we close the key, we want to see how long it's going to take until that voltage from 100 volts drop to 25 volts. So we know that the solution for that equation is that VCT is equal to VI e to the power negative T over tau. So for this one, we know that tau is R times C. So R here is 2 mega ohms. So it's going to be 2 times 10 to the 6 times C, which is going to be 2 microfarads, going to 10 to the negative 6. So it's 3. It's 3 microfarad. So C is 3 microfarads, so it's going to be 3. So it's 3 times 10 to the negative 6, so eventually it's going to comes out as 6 seconds. So if we go ahead and substitute these into that, so we have the VCT is VI, which is 100, times e to the negative t, t divided by 6. And then we want to know what's the time when the VC becomes 25. Oh, so if I go ahead and substitute the VC with 25, it's going to give me 100 e to the negative t divided by 6. And then you can just rearrange that, so it's going to have 0.25. So if I bring the 100, so it's e to the negative t divided by 6. And then if I use the ln from the both side, what I'm going to have is going to be the logarithm of 25 is going to be the ln of e to negative t over 6, and that basically the logarithm, and the ln and e is going to cancel each other, so I have the ln 0.25. It's going to be comes to the negative t divided by 6, and this one, so gonna be here. And then eventually if you do the calculation, you'll find the t would be 8.31 seconds. So basically after I close the key, it takes 8 seconds until the 100 volt until the voltage in the capacitor drops from 100 initial 100 volt to 25 volts.